And we go to the last talk of the session, which is property preserving hash functions and combinatorial group testing by Kazuhiko Minematsu. And he's here. Please go ahead and share your screen. Thank you.
Okay. Do you see my screen? Okay.
Looks good.
Okay. Thanks for the introduction. So I'm Kazuhiko Minematsu from NSE and Yokohama National University. And then the title of my talk is the property preserving hash functions and the combinatorial group testing. So this is a very basic background of what is a cryptographic hash function, such as a SHA-2 or SHA-3. They are designed ideally so that they should tell nothing about the input from the hash value. So if there are two inputs, no matter how similar they are, the resulting hash values are look different. And so in other words, they are designed so that they looks like a random oracle. But in the real world, people may want to learn some useful property on a set of the input from the set of the corresponding hash values. While, of course, as it is a hash function, we need a compression. Famous example of such hash function is a locality-sensitive hashing proposed by Induka and Motowani in 2098. It is a hash function such that if two inputs are close in some predetermined metric, then the corresponding hash values will collide with a non-negligible probability, P. And otherwise, the collision is bounded by a small probability. So such a hash function can be seen as an example of what we call a property preserving hash function, PPH function. And the non-PPH hash functions are generally randomized. Namely, there's a key that is sampled uniformly from some space over some space, and sampling is independent of the inputs. And because of this assumption, if the input is depending on the key, there is no such property preserving feature would be lost or even maliciously controlled by the adversary who runs the key. For example, the universal hash function, it is known that if the keys are sampled independently and uniformly, and there are the two different inputs, the corresponding output will collide with a small probability. However, if the adversary learns the key, of course, it is very easy to create the second input that will produce the colliding hashing values from the first input. And even it is possible to create a second collision by just running the first hashing values in case of the universal hash function. So with this problem in mind, the Boyle, Lavine, and Vaikuntana-san proposed what is called a robust property preserving hash function. Here, a robustness means that a resistance against the adversary who query the keyed functions where the key is used as the internally as a component of the PPH, or just against the adversary who possess the key. And they defined two robust PPH schemes for the gap Hamming distance predicate, which I will describe later. And the first scheme, which I call PPH1, is a purely collision-resistant hash function-based one, using a class of bipartite expander graphs. And the core idea is called subsampling. The second scheme, PPH2, is a linear code-based one, and it allows a smaller gap in terms of the parameter of the gap Hamming predicate and has a smaller hash size than PPH1. But unfortunately, it is relying on ad hoc assumption, something close to the hardness of the decoding a random linear code. And in my opinion, because of this PPH inspired the work, follow-up works, and there are some improvement in terms of the hash size and the cryptographic assumptions. But the first construction is largely overlooked. That may be because for larger hash size than the PPH2, but its hash-only construction is simple and will give us a high reliance on the security. So in this talk, I showed that there's a close relationship between the property-preserving hash function for Hamming predicate and a field, classical field called Combinatorial Group Testing, CGT. Which is a classical combinatorial problem invented in World War II, so it's quite old. And since then, it has many applications in the biology such as DNA screening, or more recently, it has been used in the COVID-19 PCR testing. And recently, the CGT has many more applications in various fields of the computer science. In fact, the CGT combined with a hash or a MAC function has been studied in the context of the data integrity protection or forensic application, such as these works, with various names, say corruption localization or MAC with detection and so on. We show that these applications of the CGT actually implements a robust property-preserving hash function for Hamming predicate, better than PPH1 of BLV19. Namely, it implements a PPH for Hamming predicate rather than the gap one, and it has a smaller hash size and has a faster hashing time. On the other hand, we also showed that the core idea of the PPH1, namely the use of a certain bipartite expander graph in subsampling, has been also seen in the recent paper of that studies a variant of the CGT problem. Okay, so this means that these two fields has a bidirectional relationships. And for the time constraint, I only focus on the first implication. So let me briefly describe, recall about what is a Hamming predicate and gap Hamming predicate. I consider the generalized one, namely the HD of two inputs, x over x prime, is a generalized Hamming distance over blocks. Blocks means that some fixed amount of bit strings. And the Hamming predicate with threshold D of x and x prime is 1 if this generalized Hamming distance is not smaller than D and 0 otherwise. A gap Hamming predicate with D parameter D and epsilon is a loose version of the gap Hamming predicate, a Hamming predicate. It tells if x and x prime are too far or too close. So as shown by this figure, so there are some gaps that where if the result is in this area, the gap Hamming predicate returns undefined. Is defined as is not defined. So to define the robustness of PPH introduced by BLV19, we first assume that the hash function having a key space k, input space x, output space y, and a two input property p. And we consider two possible oracles. The first one is the hashing oracle, which returns the hashing value for a given input. And the second one is the evaluation oracle, which returns a result of the evaluation function, taking the key k and the two hash values y and y prime. And this evaluation function is designed so that if actually these hashing values are coming from the two input x and x prime, then this evaluation actually correctly predicates the property of the two inputs. And the goal of the adversary is to produce the pair of inputs such that this evaluation function fails to predict the input property between the two inputs. And BLB19 defined 4 classes of robustness notions, but I only present the 2 strongest ones. The first is the direct access robust PPH. In this game, the adversary just has a key K, so there's no need to oracle is needed because the adversary can simulate it. And this is the strongest definition and simply called robust PPH. The second one is a double oracle robust PPH. And in this case, the adversary can access the hashing oracle and the evaluation oracle, but does not have the key. It is the second strongest notion. Let me briefly describe what is the PPH1 proposed in the BLB19. Originally, it is defined as over the bit string, but my description is a generalized one. Namely, the input consists of the n components, where each component is b bits, b bit block. And we assume the hash function g here, producing the t bit outputs for any input. And we then build our bipartite expander graph EZ having n left nodes and k right nodes here. And let S of I be the set of the neighbors of the right node I, and X sub S of I be the projections specified by S of I. Then the PPH1 for input X is a concatenation of the small k hashing values, where each hash function takes the projection specified by SI, S of I. To evaluate the gap Hamming predicate given to hashing values, it just computes the generalized Hamming distance between the two hashing values. And if this Hamming distance is smaller than a certain threshold with this term, where large D is a parameter of the expander graph, and D and small d and epsilon is a parameter of the gap Hamming predicate, then it outputs 0, means that they are close, and otherwise 1 means that inputs are far. BLB19 showed that by choosing the ADK parameters for expander graph, including large D, PPH1 implements a robust PPH4 gap Hamming for some D and epsilon. So I'm not going into the exact formula for these available parameters. So let me move to the description of the combinatorial group testing. Okay. Suppose we have n items, and that may contain at most d defectives. In the original settings invented in the World War II, the item is a blood sample, then the defective is a bad blood sample infected by viruses. And we want to try to find all the defectives by using a group test. Here, a group test means a test that returns a positive if contains the set contains at least one defective. And suppose we can use small k group tests to find these defectives. The design test experiment is completely specified by n times k binary matrix M, where each row specifies a test. Means that 0 means that this test does not include these items specified by each column. and 1 means that this item is included in this test. We say that if this matrix is D-disjunct, then any union of at most D columns do not cover any other column. That means that if we choose a set of the at most D columns here, and then choose another column here, there exists one row such that this part is all 0 and this part is 1. To detect the defectives, we performed all the tests, all the small k tests, then evict all the items included in the test that returns negative. This is called the naive decoder in the field of the combinatorial group testing. Okay, and let P denotes the remainder index set of the items. Then the disjunctness condition guarantees that this P is actually the set of all the defectives without error. Because, for example, if this set is the set of all the defectives, then this JS item, suppose this JS item is not defective, non-defective one. Then from the condition, there must exist a test such that the test result is negative while this JS item is included in this test. That means that this test excludes the JS item. If we pick another non-defective one, H, then of course there must exist another test that excludes this H item. Okay, with this reason that we can evict all the non-defectives. Okay, so using this disjunct matrix, building a PPH for Hamming predicate is something straightforward. We first use n times k, d prime, which is d minus 1, disjunct matrix m, and we prepare a collision resistant hash function g here, producing a t output bit. And let x sub m over I be the subsequence of the x specified by the ith row of m. And then the CGT hash, the output is defined as a concatenation of the k hashing hash values, where each hash function takes each subsampling specified by m of I, ith row. To evaluate the Hamming predicate, we just run the naive decoder and get the set P and output 1 if this size, the size of the P is larger than D, and otherwise output 0. So this shows that the left figure shows the PPH, original PPH1, while the right, this part shows the PPH built from the combinatorial group testing combined with the hash function. This one and this one are originally considered in the different system models, but effectively doing the same thing. The PPH1 subsampling is based on the expander graph, and property evaluation is done by computing the generalized Hamming distance of hash values. And for CGT hash, subsampling is based on the disjunct matrix, and the property evaluation is done by naive decoder. So actually, this CGT hash-based PPH works correctly. Namely, if the Hamming distance is at most D prime, this P identifies all the different blocks. Namely, that we learn the index that is different in between the two inputs, so we can correctly output what's 0. And otherwise, because the decoder's output P, the size of the decoder output P is always at most the Hamming distance of the two inputs, we know that actually this is a case. so we can safely output 1. And this property is from the property of the naive decoder, and this property is also called the strict group testing in the field of the CGT. And it is rather straightforward to show that this CGT hash is secure. Namely, it is a robust PPH whose security is reduced to the collision resistance of the underlying hash function G. And moreover, it implements a robust PPH for not Hamming property, but what we call the detect property. Namely, we can pinpoint the different blocks when the Hamming distance is at most d prime. This is not a predicate, so not a binary function. So it is more informative than the generalized Hamming predicate. And I have to mention that there's a limitation because we have to compress the output. So this equation inequality must be whole. And here the k is the number of the hash components and the number of the rows of the disjunct matrix. And it is known that the k is at most d square log m for m to be d disjunct. So that means that this scheme is only effective if d is relatively smaller than m. But such PPH for small d is, I think, still useful, for example, in the field of the biometric identification or authentication. This slide shows the comparison between the PPH1 and CGT-based construction. Direct comparison is difficult because the first one implements the PPH for gap Hamming, while the ours implement the Hamming predicate. But if we follow the parameter suggestion originally suggested by the VLB90 paper, we can show this table. And in this table, we assume that each hash function is order of n time. And we assume that the disjunct matrix used by the CGT hash is the order optimal, in smallest number of rows in terms of the order. And such disjunct matrix can be built with known techniques. I'm not going into the detail of the explaining each figures, but this output size shows that generally, if D is sufficiently smaller than N, our scheme produces a much smaller output length than the PPH1. And there are some more results. The first one, if we change the hash function, if we use a MAC function instead of the hash function, then this implements a property preserving hash function of the security for the property is double oracle robustness. The proof is almost the same as in the case of the hash function, but if we use a MAC function, we can use a trick of this paper that allows us to reduce the hashing time significantly. And there's another paper that also reduces the hashing size significantly, even beyond the limit of the disjunct matrix. But this is possible. We are exploiting the linearity between the MAC tags by using a specific type of MAC function. But proving the double oracle robustness for this type of function is still open. Maybe possible, but I have not found a way so far. So to conclude, this talk shows nothing new, but just show a connection between the two independently studied fields. The first is the PPH for Hamming predicate, and the second is data integrity or forensic application using CDT. And we show that the non-CDT combined with the hash or MAC function schemes provide better constructions for PPH for Hamming predicate. And as I omitted in this talk, but the core idea of PPH1 is also seen in the CDT matrix construction of a certain type. So I think it may be interesting to further explore the relationships between two fields. Okay, that's the end of my talk. Thanks for your attention.
Thank you very much, Kazuhiko. Any questions? The break is also short, so if there is no questions, I can ask one very quick question. Maybe I'm missing something extremely simple and stupid, but nevertheless, let me ask. Is the definition of the property preserving hashing necessarily gonna be a computational primitive, or could it be information theoretic? I mean, of course, you use information theoretic tools like group testing to construct this, but I guess the final constructions still use CRH somewhere, yeah?
Yes, that's
And is
my idea. So in that case, we at least need a collision resistant hashing function.
your construction does need it, but the definition of this primitive, it wants two things that are close to have like close collisions. It's not at least immediately clear why it can't be information theoretic, but
yeah, I have no clear answer, but they are with a certain, I think with under some natural condition, we must need, we can show that we must need a computational, primitive.
Okay.
Yeah.
Okay. So, okay. Thank you. If there is no other questions, let me thank Kazuhiko and all the authors of this session. And I think we're gonna resume pretty soon for Yuval Stack. Thank you, everyone.